So in order to talk about the fracture of materials, the failure of materials, we need to have a discussion about strain energy. And so we're going to start our discussion of strain energy in one dimension. So now we have our rod here, and we're going to pull on our rod, and sometime later our rod is going to be slightly different length, and I'm going to call that change in length an amount d delta. So little delta here, some deformation. We have some kind of load on our rod here, and it starts off with some length L. It's going to be L there, and it has some cross-sectional area A. Okay, so, the standard stuff. And what we want to do is we want to figure out how much energy we've stored in our rod. So if you remember back to the idea of Hooke's law and thinking about springs, if you pull on a spring, you store energy in it, right, as elastic energy. And what we can do here is we can say that the change in internal energy, I'm going to abbreviate that, is going to be equal to the work that's done by the external forces, right? That's one of our relationships in physics. And so what that's going to look like in our case is we'll have some amount, so that's going to be dW, so that's some increment of work. And we're going to have that equal to P, which is the load that's applied, times our displacement, which would be, in this case, d delta. So just to go back here, this would be our increment of work here. So this is going to be the work. There we go. This is going to be our external load. And this is going to be our displacement. So that all works out. And what we really want to know is what is the work that's done to stretch the rod some amount, which we'll call delta naught. Okay, well, we want to know the total work. So what does that mean? Well, we need to integrate the increments of work, the dW's, and that would look like the integral from 0 to delta naught of our expression here. So that's P d delta. And now what we need to do is think about what P is in terms of our material and what d delta is in terms of our material. So we can do that. Remember, we always have some tools in our toolbox, and so we can use those here. So the first one is equilibrium. So what does equilibrium tell us? Equilibrium says that stress is equal to the applied load over the area, which means that P is equal to the area times the stress. And that's going to be useful for us. We know where that's going to go. The other thing that we know is we have some relationships for kinematics. And in that case, if we have some displacement, d delta, there's a d delta there, we know that that's going to be equal to some strain, which I'm going to call d epsilon. So that's going to be some small increment in strain times the initial length L. So again, we're just saying deformation is equal to strain times length. That's great. Well, look, now we have some things that we can plug into our equation over here. So now we have the work done is equal to the integral from 0 to delta naught of the stress times A times L times d epsilon. And we're going to need to rearrange some things. We have work here, we have A, we have L. We're now going to have to integrate over strains. So now we're not going to go to delta naught, but we're going to go to epsilon naught, which is some strain. And we'll keep our sigma in here. and we'll have our d epsilon, our d strain. And if we think about the different pieces of this equation, we can kind of put this together. So this is going to be energy in the form of work, right? And this quantity, the area times the length, is going to be some kind of volume. And so what might be interesting is to think about what's left. And what we're going to call that is U. And it's equal to the integral from 0 to epsilon naught, so some strain of sigma d epsilon. And what we're going to call that, because we've got to have names for everything, is strain energy density. And based on what we just talked about, we kind of understand what this quantity is. It's going to be some energy divided by the volume. So this has units of energy divided by volume. And that's why you get an energy density. Okay, so that makes sense. That's good. And what does that look like for us? We've been drawing these stress-strain diagrams, and we typically have strain down there and stress down there, and we might have some curve like we've been drawing that has a nice defined yield plateau and some strain hardening, and eventually comes in fractures. And what this strain energy density is saying, okay, we integrate from 0, which would be here, to some strain, let's call it here, that would be epsilon naught, the stress as a function of epsilon. So if we integrate our curve, we're going to get the area here. And so when we talk about strain energy density, all we're really talking about is the area underneath the curve. So U is equal to the area under the curve. And so now there's a couple of different areas that we might be interested in characterizing for different materials. And so the first one, we'll draw down here. So we're going to use our same example for steel. We're going to have a curve that looks something like this. And we have stress on this axis and strain on that axis. And if we go just to the yield point here, so this is our yield stress, and we look at the area here underneath the curve, that area we're going to call the modulus of resilience. And essentially that's just the energy that the material can absorb before it yields. And if you want to calculate the strain energy density while the material is still elastic, so as long as the two stress and strain are proportional to one another and related by the elastic modulus, you could say that the area is just going to be 1/2, because it's a triangle, times the value of the stress times the value of the strain. And that would be just the area of the triangle. Because we know the relationship between stress and strain in the elastic portion, this ends up being 1/2 the elastic modulus times the strain squared, which should look a lot like the spring energy if you go back to your physics class in Hooke's Law. Okay, so that's the modulus of resilience. It's just the area up till yield. The other one that we might be interested in characterizing, I draw my picture here again. Here's strain, here's stress. Here's our stress-strain curve, is the total amount of energy that the material can absorb before it fractures. So now we're going to calculate that whole area, And that area we're going to call the modulus of toughness. So this is going to be the strain at fracture here. And you can see this is the total area under the curve. That's a V there. And you can also see, if you think about going back to our brittle versus ductile materials, for a ductile material, the modulus of toughness is much larger than the modulus of resilience. You can see the two shaded regions here are much different in size. For a brittle material, what do these pictures look like? Well, a brittle material will come up straight and then will fracture. So we might actually be elastic almost all the way to fracture. If we calculate our modulus of resilience and our modulus of toughness, we might find that they're very close together. So that's just one more way that we can think about the characterization between brittle and ductile materials.